Good morning, afternoon, or evening. This is Professor Rodriguez, and these are two exams that were prepared for the Stat 1 and Stat 2 sections of the undergraduate class in statistics, and I'm also offering these to the grad class as practice and a self-test for problem solving. So let's begin with, what you see on the left-hand side is the exam of one class, and what you see on the other is the other class. So I'll actually review both of these at the same time. All right, so we have this question. The average salary for 10 managers was $85,000. That's the average salary. One manager leaves the company. Well, okay. That leaves us with 9 managers. And that changes the average salary of the remaining managers to $90,000. So these managers, who are the remaining managers, average $90,000. What was the salary of the manager who left? Well, so we had 10 managers making $85,000 apiece. So all 10 of them were making $850,000. And now we have 9 managers who average $90,000 apiece. So if you were paying 9 managers an average of $90,000 apiece, you would be paying them $810,000. So now we're paying 9 managers $810,000, and that means that we used to pay $850, now we pay $810, and the difference there is $40,000. And where did that $40,000 come from? It came from the person who left. So what was the salary of the manager who left? $40,000. So let's, a similar question on the right-hand side. The average salary for 10 managers was $87,000. One manager leaves the company. That means we have 9 managers. Changing the average salary of the remaining managers to $90,000. What was the salary of the manager who left? Well, we used to pay 10 managers an average of $87,000, which means we had to budget $870,000 for this item. And now we have now we have 9 managers, again, 9 managers making an average of $90,000, so we have to budget $810,000. And what's the difference between those? It's $60,000. And where did that $60,000 come from? It came from the person who used to be up here, but is not down here. Is not a member of the 9. So that's the way you do a problem like that. Question number 2. The set below lists the number, and now we're on the right, left-hand side, sorry. The set below lists the number of employees in 5 different departments. What are 3 measures of central tendency related to these numbers? I'm not asking you for generic 3 measures of central tendency. Well, they're mean, median, and mode. I'm asking you for the 3 measures of central tendency that are related to these numbers right here. Okay, so what are the three measures of central tendency? Let's order them first. We have 18, 22, 22, 26, and 75. So, one measure of central tendency is the median, the one in the middle. So, one is the median, which is 22. Another measure of central tendency, but particular to these numbers, is the mode of 22. The next is the mean of, so let's total this up quickly. So we have the 5 and the 6 is 11, 12, 13, 14, 15, 15 and 8 is 23, 3 carry the 2, 2 and 7 is 9, 10, 11, 12, 13, 14, 15, 16, so we have 163, and there are 5 numbers here, so well, I didn't mean for that to happen. So the average number here is well, let me double check that. Is it really that high? Yeah, it is. Okay, so 5 into 16 is 3, and then 1. 5 into 13 is 2, is 10, and then we have 3 left over, 3 over 5, right? Or 32.6, 2.6, and, sorry. So 32.6, that's the mean. Okay, so you have these three measures now. Now the question is, which of the three would you argue is the best to capture what is normal in this group, and why? Well, so I actually didn't consider one as being more correct than the others. I wanted you to give me a reason why, and that was good enough for me. So if you said it's the median, you would say that you have this outlier, 75, and the median best captures what's kind of central to these numbers. If you said the mode, how did I do this 22? I'm looking at another. So the mode here is 22. So you would say, well, it's most likely in this group, so that's fine. If you said the mean because it captures all possibilities, then I think that's a fair argument. Look, if something happens 1 out of every 5 times and it's some kind of crazy thing where you expect something to happen in the 18s to mid-20s, and every 5th time some 75 crazy thing is going to come up, then you wouldn't want to exclude that 75. So I guess I was tolerant of that answer. So on the other side here, on the right-hand side, it's the same question, but with different numbers. So we have an 18 here, and then a 20, and then a 20, and then a 26, and then a 75, and that's where I got those 20s from on the left-hand side. So you would say the median equals 20, the mode equals 20, and then the mean equals 20 and 20 is 40, 50, 50, 60, 70, 84. So we have 84 here. And the 75 is 915. So 5 into that is 3. And then 1.8. And the same as on the other side. If you had a good argument to support your selection, that was good enough for me. Although it makes sense to me that the mean really doesn't represent, I don't think that well, but there would be situations where you would not want to exclude the mean. The mean would be an important number. Okay, so question number 3 on each side. On the left side is, assume that an employee's productivity score is measured based on a combination of 3 different tasks according to the following weighted scale. So these are weighted scales and probabilities. Some tasks are more important than others. Calculate the productivity score for the following employee. So this is like saying you're taking a course and the weight of task number 1 or assignment number 1 is 50% of your grade. The second one is 35% and the third one is, well, guess. It would be, well, your grade's going to be made up of 100% of something. So if there are only 3 tasks that go into this assessment, then the first is 50%, the second is 35%. That must mean that the third is 15%, which is what it is. And then, so now you would just multiply every weight, which is actually equivalent to a probability, times the score. So you would say 0.5 or 50% of 94 is 47. I have something to say about that in a second. And then we have this 35% of 89. So let's take 89 and multiply times 35. So we have 5, 40, 44, and 7, 2, 2, 6. So we have 5, 11, 31. So we have a 31.15 here. And then we have 15% of 83. So 83 times 1.5. And, okay, I'll do this a long way. I don't want to confuse anyone. So you have 15, 41, and 83. So we have 1, 2, 4, 5. So 1, 2, 4, 5. So we have 0.60 here, and we have 10 here, 80. So the answer there is 80.6. That would be the productivity score. You know what? Check my own math here. This is a 9. Now, okay. So I did that on purpose. And the reason I did that on purpose is because lots of students make that mistake very easily. As a matter of fact, in the class that took this exam, just about half of the class made quick computations, and that led them astray. So let me tell you what an easy fix is to this. So let's say we still had the 80.6 there. We have the 80.6. Now what would we look at? We would look at, how did I get this 80.6? Well, I have 3 scores. One was a 94, one was an 89, one was an 83. And now I would be thinking, wait a second, how could my average be lower than any one of my scores. It can't be an 80. So let me go back and check my arithmetic. And then you get the 10 here, and then the 6, and that's 0.60, and 7 and 1 is 8, and 2 is 10. So that gives you a 10. You carry the 1, so it's 1 plus 4 is 5, 5 plus 3 is 8, 8 plus 1 is 9, and you get the 90.6. Good? So that would be the productivity score. Now, on the other side, we have the same thing, different numbers. But then again, these are weighted scales, which you would look at the same way you would look at probabilities. As a matter of fact, this is easier to do, and of course, what that means is it's easier to make rushed mistakes. So if 100% of our score is made by these 3 assessments, and one of them is 50%, the other is 30%, well, the other one is 20%, right? Okay, so then we have 50% of 92 equals 46, and then 30% of 89 equals 26.7, and then 20% of 83 equals 16.6. And then you total that up, and the 7 and 6 is 13. And of course, this is like a 0, right? So the 7 and the 6 is 13. And you have a 6, 6, and a 6 here. Oh, no. Okay. No. Guess what? Well, okay. It's horrible. So you have 3 6s there. So the 3 6s is 18, and the one you carried is 19. And that leaves 1 that you carry, and then the 4 and the 1 is 5. And then the 2 and the 5 is 7. And the 7 and the 1 is 8. And then you have an 89.3. You wouldn't round up. You couldn't. So, wow, that's a heartbreaker, isn't it? So if on this third assignment, by the way, that would be an excellent question, wouldn't it? So the question would be, by how much would your third grade have had, on task 3, have had to gone up? Or if let's say my raises are based on this scale. So by what would any one of these measures have to go up in order for me to get a 90 and maybe get a higher merit raise? So that would be a great question. Okay, so now let's go to the left side and do 4 on the left side. Oh my goodness. Yeah, this was so easy for people to make errors. And really careless errors when you think about it. Okay, listen up, you DBD people. This is what I'm saying. I'm saying I've given both of these exams this semester, and entirely too many people, when they were ordering these numbers, left out a number or 2. And you can't do that. You need to count your numbers. So Wait, the first thing you would do here is you would put these numbers in order, right? Because it's going to ask you the interquartile range. And you can't do that very easily. So if you're looking at interquartile range or percentile, you need to put these numbers in order. Okay, so let's go from left to right is negative, from negative to positive. So the lowest number here is minus 825. The next lowest number is this minus 675. The next lowest number, and this is easy because all we're looking for is negatives, right, is minus 212. The next lowest number is minus 136. Now all we have is positive numbers left. So let's look at the lowest positive number is a 24. And you know what? I'm going to put lines under these because otherwise it would be, it's easy to lose sight of it. So 24, then go to the next one would be this 86. And then the next highest one would be this 157 over here. Then the next lowest one would be this 180. Then the next lowest one, did I X out the 80? Yep. The next lowest one would be 237. Sorry, would be 237. The next lowest one, let me X this out, would be 247. Sorry, this is entirely too sensitive. 247, 237, 247. The next lowest one would be 519, and the next lowest one would be 882. Okay, listen up, because here is where we're going to prevent some errors. We're going to count the numbers on the top, which we need a count of these numbers anyway, right, to figure out what the median is and what the interquartile range is. So let's count them. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. Now let's count the numbers that we wrote down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That was simple, wasn't it? Okay. Now what we do is we need the median. So the median is the one in the middle. In this case, 6 and 7 are the two in the middle, right? So, in other words, we have 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4, 5. So here are the two in the middle. So the median would be both of them added up and then divided by 2. So we have 13, 14, 2. So the median is 121.5. And again, do a double check. Is 121.5 kind of between 86 and 157? So you could look at the 86 and 57 and just ballpark it. Oh yeah, it is, looks like it's in the middle. All right, so now you have the median. Now you can split this up into two groups, right? You have 6 on this side and you have 6 on the right hand side. So Now let's divide those 6. And when we divide those 6, we have here, this is 3, and then we have 1, 2, 3 over here. So, optimally, this is what you would do. You would take the mean of the minus 212 and minus 136, get the mean of that, then you would take the mean of this 237 and 247. Well, the difference there is 10 points, so just split the 10 into 5, and you know the mean there is 242. And then you would say the interquartile range is, what was this? Okay, so this is 348, 348. Okay, so that is 174 minus, and this is a plus, and so you subtract these numbers from each other, and that's what your interquartile range is. It's the distance between these things. In other words, the 0 is here. The 174 is 174 units to the left side, and to the plus side, you have 242 units. So how many units do you have between these things? So the units you have between these things is 6, 11, 4. It's 416. Okay, that's the interquartile range. All of that work for what? What's the question here? Okay, what is the interquartile range? We've got it. It's 416 points. Why would it be better or worse than the full range to capture dispersion? Okay, so if we're going to say 416 is different. What's the full range? Well, it's the 885 on this side, on the minus side, and 882 on the plus side. So you have, wow, so you have 1707. Oh, there's a big difference between 1707 and 416. So the question is, which one is best? And the answer is, you could have said either, as long as you defended it. So how did people defend it and get credit? So one way to defend the 416 is to say you have these big outliers, and the outliers are really skewing the data, so we're not going to include the outliers. So why would you argue that the 1707 is better to measure dispersion? Well, because if you're talking about money, outliers are important, right? So my choice, my decision on whether to use the range or the interquartile range would depend on my assessment of whether those outliers were the result of very rare occurrences or of something that happens typically. So we know, of course, that retail stores lose money all year round, except for the fourth quarter. So that's a big deal. So you wouldn't want to exclude outliers because outliers are important. So that's the answer to that question. And on the other side, you could do exactly the same thing, except look at this. Wow, on the left-hand side, I gave you a really big outlier, minus 2825. So, but again, Exactly the same response. All right, number 5. In a department, 20% of the employees are rated excellent. Good. That's good. So 20% of the employees are excellent. 1 out of every 5. Let's do it this way. Out of 100 employees, how many are rated excellent? 20 of them, right? 20%. Assuming independence, that is that being excellent and being from an Ivy League program are not related. Obviously, Ivy League programs would argue with that. But assuming independence, if 7% of all employees, 7% of all employees are rated excellent and come from an Ivy League program. In other words, these 20 get down to how many? 7%. 7. Determine the probability that any department employee comes from an Ivy League program. Well, how many people of an Ivy League program who are excellent come from an Ivy League program? Well, you can see that's 7 over 20, or 35%. So 0.35 or 35%, they're both fine. So the probability that any department employee comes from an Ivy League program is 35%. Okay, so 6. Let me see if this is, so 5 on the other side. It was the same thing, different numbers, right? 20% are rated excellent, assuming independence. 5% are both excellent and come from an Ivy League program. So what is that? Let me go back to this. 20% goes to 5%. So what does that mean? That means 5 out of every 20, right? 5 out of every 20 is what of every 100? So it would be 25 of every 100. So this answer here is 25%. I don't know why I'm losing the ink on that side. Well, there you go. Came back. All right, so question number 6. What percentage of a company's workforce is expected to have a salary higher than 1 z-score of the average? Again, it's so easy to make mistakes because you're going too quickly or not forcing yourself to think step by step. So the first thing we do here, we're looking at a z-score and we're going to look at the space underneath the normal curve. So what are we going to do? We're going to draw a normal curve. And a normal curve has an average here. And a 1 z-score means 1 standard deviation. And it's plus, so it's the 1 standard deviation on the right side. So the question is, what percentage of a company's workforce is expected to have a salary higher than 1 z-score? Okay, so we have higher than, lower than 1 z-score, but higher than average. And then we have higher than 1 z-score. Now what we know is that this, in a normal curve, divides or distributes your ends into two groups, and each is 50%. You have the 50% on the south side, 50% on the north side. And we know what one standard deviation is, don't we? So it's 34%. In other words, we know that all on this side is 50% and lower than one z-score, but on the north side of the mean is 34%. So the rest has to be 16%. So if you said 16, 17%, good enough. So the answer here is 17%. Or 16%. All right, question number 7. Assume that a retail chain has employees whose ages are normally distributed with a mean of 25. Oh my goodness. We're doing the same thing again. So we have this normal curve. And we have one standard deviation, two standard deviations. We have the mean here. Okay. A mean of 25 years and a standard deviation of 3 years. That means one standard deviation would take it up to 28 and another standard deviation would take it up to 31. And then on the south side, one standard deviation south of the mean takes us to 22 and then to a 19. Okay, now folks, the question is this. Calculate the expected percentage of employees who are between what? 19 and 28. Okay, so we have all of this and this. Well, so how do we do that? Two standard deviations on this side capture what? Well, if two standard deviations on both sides is 95%, two standard deviations on one side is half of that, or 47.5%, or 0.475. And if the standard deviation on one side of one, standard deviation of 1 captures 34%, then that means that captures this. So all we need to do is add these up. So we have the 0.475 and the 0.34. So you see 81.5%. That's the answer to that. 81.5% or 0.815. Some people, based on their estimate numbers, instead of taking a 34, they took 33. That's fine. That doesn't bother me. So it was 80.5. That's fine. Okay, so that's question number 7. Question 8 is this. To determine whether a new training program was effective, some employees were trained either method A or no training, and their productivity was subsequently measured in minutes. Okay, so what are we saying here? Well, let's do the model right out front. Let me erase this. I don't know how that keystroke got there. Okay, so let's draw the model, because models are helpful. I mean, it's a visual representation. So what are we saying here? We're saying depending on the training method, you'll have a different effect on what? Productivity. Good. That's your model. Some people were tempted to do training method A and then put no training down here. And you see how that unnecessarily complicates the visual representation. You don't need to do that because no training is a training method. So depending on your training method, that determines your productivity. What's the independent variable? The independent variable is the box with no arrows leading to it. It is independent. Nothing affects training method. It's the thing that you start out with. That's the independent variable. What's the dependent variable? The dependent variable is productivity. That is, you're saying that productivity depends on the training method. So this is hypothesis testing and models. Okay, so question number 9 is a weighted probability, and I went over this several times in class. I'll tell you, it's easy to get wrong, so you really have to pay attention to this stuff. Okay, so weighted probability. So how many people will tend to get out of 100? How many people will tend to get 0 dreams? 22. 22% will get 0 dreams. So what's that? 22 times what? Times 0 equals 0. 11% times 1. So that's a 0.11. 24% will get 2. So that's 0.48. 31% will get 3. So that's 0.93. 12% will get 4. So that's 0.48. So you have this much, this much, this much, this much, and if you total that up, you should get 11, 19, 20, 0, 6, 15, and 15, right, so this is 2.0. Okay, so the probability, here, these are key phrases, right? Probability, distribution, and now you have various probabilities. In other words, various likelihood of different outcomes. How many defects should we expect a trainee to produce during training? So that's what it looks like. So the answer is 2.0. Takes us to question number 10. What is a type 1 error? Okay, a type 1 error is a false positive. A number of people said false positive is good. What does that mean? It means you conclude that something you conclude that your hypothesis is true when in fact your hypothesis is not true. And that can happen because you use a test that favors, maybe unfairly, biases the results, or you set a low standard of finding something to be true. So a type 1 error is a false positive. So what's a type 2 error? And that was a question on the other exam. So a type 2 error is a false negative. That is that is not concluding the positive, falsely concluding for the negative, which in this case is the null, when the positive has weight, significant weight, leaning in its direction, but you're just so conservative that you will not find something to be true, even though it is true. So that is hypothesis testing. And that takes us to 11. What is alpha and what is a typical standard? This is hypothesis testing again. In psychological, sociological research, what is the practical consequence of this standard? Look, it's easy to take a course like this and see questions with numbers all over the place and say, this is what I have to learn how to do. This is what's going to drive me crazy. Let me caution you. You can do all kinds of calculations. If they're the wrong calculations based on the wrong assessments, or you're following steps incorrectly, running the right numbers to solve the wrong problem will not be helpful at all. So you really need to pay attention to hypothesis testing, because it means you have followed steps that everyone assumes to be correct steps, and they are logically integrated with each other. So it's defensible. Okay. So, therefore, what is alpha? Alpha is the amount of error you're willing to tolerate. And in social psych research, alpha is 0.05. And what does that mean? Well, it means 5 out of 100 times we're accepting something to be true that probably is not true. So 5 out of 100 is 1 out of 20, so it means 1 out of 20 times we're accepting something to be true that, is not true. So does that bother us? Well, no, I don't think it bothers us so much, because after all, we are defining our error. So we know what our error is, and that's an important thing. Okay, so 12. A researcher hypothesizes that H1, men receive higher starting salaries than women. What's the null? Okay, here's the magic phrase. It is not true that, and then just fill it in with the hypothesis. The null is not the negative, the null is not the opposite of the hypothesis. The null is the absence of the hypothesis. So the absence of men receiving higher starting salaries than women is not that women receive higher starting salaries than men, because it also could be that their salaries are equal. So there are two potentialities if the hypothesis is not true. And it could lead you into perilous waters if you try to do that on the fly, especially if the phrasing of the hypotheses are tricky with double negatives or subordinate phrases. So it's just easier to say, it's not true that, and then copy the hypothesis. And I believe that's it. So for the sake of the DVD, folks, you should have this stuff really nailed down. I encourage you to talk to one or two of your teammates, study together. If you have any questions on any material, ask each other, work through it together. and learn. That's what this is all about. So good luck to you, and this video, of course, will be helpful for the stats for HRM folks as they review how they did on their exam. Thanks. Have a good day, night, and I'll talk to you later. Bye.